Thank you very much for the invitation and the introduction. As said, I would like to talk today about convexity inside symplectic geometry, and more specifically about the behavior of certain symplectic invariants in symplectic geometry and the behavior in convex domains. Let me go back and start with kind of the origin of symplectic geometry, which comes from Hamiltonian dynamics. What I mean by that is that one can represent classical mechanics in the phase space by taking coordinate systems of the Q and P, the position and momentum, and choosing some Hamiltonian function, which will represent the energy of each point in the system. And then the Hamiltonian equations will describe the evolution of the system throughout time. And it will give us a flow on the space. And for example, if we take Hamiltonian to be the kinetic energy plus some potential energy, we will recover this way Newton's second law. And a feature of this system would be that it's volume preserving. So meaning that the Hamiltonian flow we get from this way would actually be an area measure preserving map. And it turns out that much finer quantity is being preserved, and that would be the standard symplectic two form, so a non-degenerate closed two form. And any Hamiltonian flow would preserve this quantity. And it is a stronger requirement than being volume preserving because omega naught to the power n is a volume form. And in R2n, it's turned out that a symplectomorphism, so a map which preserves omega, it can always be represented as coming from some Hamiltonian. So it could be represented as a Hamiltonian flow. So this creates a kind of strong motivation to study symplectic maps. And one can kind of generalize this story into an arbitrary manifold. So we take an even-dimensional manifold, and if we can equip it with some closed and non-degenerate two form, so we call it the symplectic form, then we can recover the same procedure. So if we have some function on the manifold which represent the energy, then using our symplectic form, we can get a flow by requiring that omega of the flow would be in correspondence to the differential of H. And it is similar to the classical case because it's energy conservation. So this flow would stay on the level set of the Hamiltonian. And moreover, this flow would be a symplectomorphism. So it will give us a map which preserves omega. And this is already an indication on the richness of symplectic maps. So we can get a symplectic map for any Hamiltonian we can construct. And this suggests that the space of symplectomorphism is kind of infinite dimensional, somewhat in contrast, for example, to the Riemannian isometries from Riemannian geometry. So this is a way kind of a bigger class. And kind of a natural question one might ask is, how can one distinguish between two symplectic manifolds? So we know that they must have the same volume because any symplectomorphism is volume preserving. We know that they must have the same topology. But a classical effect is that there is no local invariance. So this means that we can kind of choose charts on the symplectic manifold which takes the manifold to be started the standard R2N case, so this classical phase space. And this means that we cannot have a hope to find invariance in a local way. And for a while, it wasn't clear whether there is anything else. So meaning that there was a question whether one can approximate any volume-preserving map with a symplectic map. So meaning how essentially different symplectomorphisms and volume-preserving maps are. And this question was resolved with the famous Gromov non-squeezing theorem, which states that a ball of radius r can be symplectically embedded into a cylinder of radius r if and only if its radius is smaller, so meaning if and only if the ball is already lying inside the cylinder. So this means that the symplectomorphisms are very different from volume preserving, and we have some global invariant to a symplectic manifold, which is different than the topology or the volume, and essentially that would be sort of the symplectic invariant we would like to study. So how could one turn this story into a more quantitative thing? Is you can define the Gromov width, which asks kind of what are the biggest ball one can symplectically embed into a manifold, and the cylindrical capacity, which asks what's the smallest cylinder we can embed our symplectic manifold into. And the non-squeezing tells us that these numerical values have a non-trivial value. So it's not kind of an easy thing to know what the value should be. And we call this thing asymplectic capacities, and we can actually generalize them and define them in an axiomatic way. So we will work in R2N throughout the talk, so we'll define it only in this case. So for a subset of R2N, we define a capacity as kind of a size of a symplectic set, or of a convex of a set, sorry. And because we want to think about it as kind of a set, we want it to satisfy the following conditions. So we want it to be monotone. So we want the size of one set to be smaller than the size of other set if we can kind of symplectically embed it in one another. We also want it to behave nicely with respect to scaling. So if we scale a subset of R2N by alpha, this means is in correspondent to multiplying the symplectic 2 form by alpha square. So we want the capacity to also be multiplied by alpha square. So this is where the conformality axioms come from. And we also add a normalization condition, which will guarantee that this global numerical invariant does not come from volume. So we want the capacity of a ball and the capacity of a volume to have the same size. Okay, and from the monotonicity definition, we immediately get that this Gromov width is the smallest capacity there is, and the cylindrical capacity would be the largest capacity one could get. So every capacity is between these two. And maybe let's do an example. So if we consider an ellipsoid, so up to a linear image, we can assume it takes, a symplectic linear image, we can assume it takes the form of Qi plus Pi over Ri is smaller than 1. Yes. Thank you. We can assume that, and then if we look at the ellipsoid we get, and we want to consider the biggest ball simply lying inside of it, it would be of, so assume we arrange the radiuses, and then we assume that the biggest ball inside would be of radius R1. So the Gromov width is bigger than the ball with radius R1. But this ellipsoid is also lying inside a cylinder of the same radius. So we got that the capacity of this ellipsoid is bigger than pi r1 squared, but also smaller than it. So it's equal to that for all capacities. Okay. And capacities could be actually sensor introductions in the 90s. They were defined in many different ways and using various tools, so not just like the embedding ones. And this suggests that you can use kind of various tools from symplectic geometry coming from Hamiltonian dynamics or homology theory or generating function and so on to study rigidity phenomena using these tools. So they're a very useful tool and kind of fun, but their big caveat is they're very hard to compute in general. So we, given a general manifold and some capacity, we usually do not know how to calculate it. So not everything is easy as this ellipsoid's case. Okay, so let's do an example for a capacity. So it's one of the first ones to be introduced, the Hofer-Zehnder capacity. Again, for a subset of R2n, how is it defined? So we want to consider Hamiltonian functions associated to this subset A. And we want H to be 0 in some subset, open subset of A. So here it's U, I guess. And we want it to achieve its maximum, M of H, at neighborhood of the boundary of our set, so A. Or in other words, outside of some compact subset in the drawing C, we want the Hamiltonian to be constant and equal to the maximal value, so M of H. And H is varying between these two values. And another condition we want this H to satisfy is that all periodic orbits of the Hamiltonian flow associated to this H must have period bigger than 1. Okay? And then the capacity would be defined as the supremum over all such H and the maximum of the value of H. And I'm claiming that this quantity kind of captures the size of a set. And why is that? So if we think about, say, A was very, very small and M of H was very large, then because it has 0 in its interior, it would have that the Hamiltonian must grow really, really fast. And that would mean that my Hamiltonian periodic orbits are also fast, so they would have a short period. So I cannot have a fast-growing Hamiltonian with only large periods. That's sort of maybe the intuition to why this quantity is measuring the size of a set. And if I have a large set, then I have a lot of room to grow, so I can have my differential of H growing slowly, so being small, and then maybe I could have a Hamiltonian function reaching a large value, but without a periodic orbits of a small period. Okay, so why is this thing a capacity? So it's only defined using a symplectic property, so it's invariant under symplectomorphism. And any H which would be acceptable for a set A would also be valid for any set containing A. So this gives us monotonicity kind of automatically. And also one can find a one-to-one correspondence between the H which fits A and the Hamiltonians which fits some scaling of A. So it is not too hard to see also why is it satisfying the conformality condition. However, the hard part would be to show the normalization, actually. So to show that the Hofer-Zehnder of the ball and of the cylinder is equal and equal to pi. Okay, the easier part would be to show that the Hofer-Zehnder of the ball is bigger than pi, and for that I just need to give you an h, which is the following one. So it's up to smoothing and making some small changes, but I'm taking superroom, so I'm allowed. It would be pi times the norm square in the interior of the ball and pi outside the ball. And in this case, how will the Hamiltonian periodic orbits would look like? So they would move in kind of circles and will stay in complex planes. So they will be kind of the Hopf links associated to the Hopf vibration of a ball, one can think of, and all the rescaling. So this would, well, what happens inside the interior of the ball, and would be kind of fixed points outside. And the length of the circles would be sort of 2 pi r inside, and the rate we go along the orbit is also 2 pi r. So the periods of all the closed orbits, which are at every point, would be 1. And so it satisfied these conditions. And also it seems like a very efficient way to do it, because we used all the space, so all the points have periodic orbits of period 1, so we cannot sort of find a way, maybe a place to increase the function. Also all the periods are 1, so again, we cannot find a way to shorten it. So maybe this is convincing that this is really the optimal h. And sort of what happens when we take a different domain, so say some convex domain. So I'm claiming that it should be like the h, which will be the best here, will give us the domain as a sublevel set. So again, if we have some convex domain K, and my h is such that it's reached the maximal value not in the boundary, then I could imagine that I want to make my h achieve its maximal value on the boundary, and then my derivative would be smaller. So potentially, I could only gain by that. So I could only make my periodic orbits slower, because my differential became smaller, so I could make my periods longer. So potentially, I could also, if I make this, and maybe I could also increase the value of h. So this suggests that if I reach my maximal value only on the boundary, that my h that I want to choose would be such that the domain I'm calculating the capacity to would be a sub-level set of that Hamiltonian. So the claim is that if K is convex, these Hofer-Zehnder capacity is achieved by Hamiltonian such that K is a sub-level set of that. And okay, this might be like an intuitive explanation to why this works, but actually the proof of that this is indeed the optimal for the ball and the optimal for general convex domain would be much harder and would involve using an infinite dimensional min-max techniques and procedures. So it's not just drawing pictures in order to get this. Okay, but this gives us a strong motivation to study the Hamiltonian's trajectories of having some convex domains. There's sub-level sets, which we call closed characteristics, these kinds of objects. So we start now with the some convex domain, and we look at the Hamiltonians that K is a sub-level set of that Hamiltonian. And then we look at the Hamiltonian periodic orbits on the boundary of that domain. And these orbits are actually identical even if I change my H up to reparametrization. So indeed, these loops are all equivalent to loops such that their velocity belongs to the kernel of omega when looking only on the boundary of my convex domains. Okay, so now I have a quantity which can be defined only using a domain, and I can kind of forget maybe about my Hamiltonian. And so how can one imagine that? So if I have some boundary of a convex domain, I look at some point at the normal, which would be up to scaling my gradient of my H, my Hamiltonian function, and then J times the normal, so the complex structure times the normal, if I think of R2n as Cn, would be tangent to the space, to my convex domain. And this would give me a vector field on the entire boundary. So the vector field of J times the normal. And now I'll look for closed orbits of this vector field. So this would be my gammas. And I could define the action as the area of a disk, any disk, enclosed by this loop when measured with respect to the symplectic form. Okay, so this is how action is being defined. And this quantity is somewhat important because many of the capacities throughout the years have been proven to coincide with the minimal action over all closed characteristic on the boundary of convex domains, and including the Hofer-Zehnder we just discussed before. Yes, I should remark that this is still maybe a more approachable capacities than other capacities, but still not that easy to compute. And the study of Hamiltonian's periodic orbits on the boundary of domains is a very active field of research for itself. So there are still many open questions here, like what are the exact sufficient conditions to guarantee that a closed loop exists, how many there are, and whether they're dense, and so on. But for our purpose, it would be enough to know that for convex, there's always exists at least one closed Hamiltonian periodic orbit. That was shown in the end of the 70s separately by Clark, Rabinovich, and Weinstein. And this means that this quantity is well defined because there's always at least one, so we can look at the minimum overall closed characteristics. I should mention that despite our notation of it as a capacity, it's not exactly a capacity. So it satisfies all the conditions, so it's a normalized and a symplectic invariant, and also scaling invariant. However, the monotonicity here is only true when we are restricted to convex domains. So if I have one convex domain contained inside another convex domain, it might be more easy to understand why monotonicity holds. So one can use sort of maybe relatively standard stuff to show this fact. But the fact that if I have one convex domain and another, and I can symplectically embed it one in the other while not preserving the convexity, so now I don't have an embedding of this convex domain, which is not convex, showing that it remains monotone is actually a very hard thing to show and kind of non-trivial. And kind of the only proof I know for that fact is by showing that it's coincide this quantity with other capacities when we are at convex domains. Okay. So I guess motivated by the fact that a lot of the capacities coincide for convex domains, there was kind of a folklore conjecture which state that perhaps all symplectic capacities coincide when restricted to convex domain. So maybe these axiomatics are enough to guarantee the value of a set when it's convex. So the Gromov width and the cylindrical capacity coincide for the convex set case. And this relates to Viterbo conjecture, which asks a kind of an isoparametric type inequality. So thinking about the capacity as size, we say we fix the volume. We look at all convex domains with volume 1, and we ask which of these domains has the largest capacity of them all. This is and the conjecture was that it should be the ball. So the ball would have the largest capacity among all convex domains with the same volume. And it can be reformulated kind of as a systolic inequality. So looking at the capacity divided by the volume, taking the powers correctly. So this would be a scaling invariant quantity. And the conjecture could be restated as saying that this quantity is maximized for the ball, which have a systolic one. So sort of Viterbo conjecture could be reformalized as the systolic ratio, or the symplectic systolic ratio, is smaller than 1. And this relates to Riemannian geometry. It can be seen as a real generalization of it. So the conjecture was for any capacity. And when we think about the minimal action we just introduced here, so this conjecture asks whether the action of the minimal bounds the minimal action over loops on the boundary with the volume. So this is relates to the systolic in Riemannian, which asks which relates an inequality between the length of the shortest geodesic with the volume of the manifold. And more particularly, if one think about the unit cotangent bundle of a Riemannian manifold, and this would be a symplectic manifold, and there the Reb orbit, or the closed characteristic, what we call, would be in correspondence to the geodesics on our Riemannian manifold. So this is indeed perhaps the motivation to call it this way. Recalling that the Gromov width was asking what's the largest ball we can embed inside, and the fact that symplectic maps are volume preserving, this implies that the Viterbo conjecture holds for the Gromov width, because the Viterbo conjecture was asking what's the ideal domain under fixed volume. So if Viterbo conjecture holds for the Gromov width, the first conjecture would imply the second conjecture. So this why these days it is known as kind of the strong Viterbo conjecture. Okay, so now let me point out that the fact that we use convexity here is a bit unnatural. So we are asking a question about a symplectic invariance and symplectic properties of sets, and yet we have the condition that it should be convex, which is not a symplectic property, and it's not being preserved under symplectomorphisms. And in fact, answering the question whether some domain has a symplectic image which is convex is very hard. So again, in the comparison to Riemannian geometry or volume preserving, so any domain has a volume preserving image which is convex, because there we have no obstructions. But in Riemannian geometry, convexity is being preserved under the isometries. So symplectic maps are somewhere in the middle. So the richness of the symplectic maps suggests that there are non-convex domains which has images which are convex, and yet we know that there is some rigidity. So some non-convex domain cannot be taken to be convex using symplectic maps. And there are some known results, like some obstruction to that, like coming from Hofer-Zehnder index or well invariant and some more. But this phenomenon, this rigidity of when a domain cannot be taken to be convex is not fully understood today. So maybe let me try and demonstrate this fact. So consider these two domains. So one would be the product, so say in P1, Q1 of a disk and kind of maybe a distorted disk, say in P2, Q2. So this would be one domain, and the second domain would be the ball, even though it looks like a bit ellipsoid, but it's supposed to be a ball. A union with a cylinder, and let's say chopped cylinder, so it would be finite. So this would be the union of a ball with a cylinder of a smaller radius. So I have two domains. They both are not convex. But I can tell you that one of them has a symplectic image which is convex, and one of them cannot be taken to be convex. So under no symplectic images is convex. So maybe who thinks that this one could be taken to be convex? And who thinks this one can be taken to be convex? Okay. So I can tell you the answer. So this one can be taken to be convex. So simply because I can take kind of any area preserving here, which is symplectic, because in 2 dimension, the only obstruction to symplectomorphism are area preserving, and an area preserving map here, which will take it to be, say, the standard disk, and their products would be a symplectic map in dimension 4. So from a symplectic point of view, this is equivalent to the product of disks, and in fact equivalent to a cube, standard cube. Okay, so this could be thought of this way. However, this domain, so if we think about the minimal action of this domain, so the minimal action of the cylinder is one which goes around the base of the cylinder, and its action would be sort of quarter pi, right? So this means that if this was convex, the Z capacity of it would be bigger, would be smaller than that, because it has one periodic orbit with this action. However, this domain contains the unit ball, and the unit ball have Hofer-Zehnder capacity pi. So this means that the kind of Hofer-Zehnder capacity of this domain is bigger than pi from the monotonicity. So this implies that for this domain, the EZ capacity and the Hofer-Zehnder capacity do not coincide, which we know happens for every convex domain. So this means that under any symplectic map, this domain could not be taken to be convex. So maybe this is some way to try and emphasize this point. But you may say, okay, so maybe you should not take convex here. Maybe you should take some different set. So maybe let me try and justify why we take convexity. So it is not true for not convex. So if we go even to star-shaped domains, the conjecture is no longer true. So, and in fact, the strong one fails like completely. So, and with a very nice domain. So maybe let me describe the domain. So I can think of a map from C2, say, to R2 plus. We call this the moment map, which go to the norm of each of the coordinates. And now I can look in R2 plus and construct the domain and look at the inverse, and this would give me a domain in R4. And I know that if it's contained the point 1, 1, meaning containing the torus in dimension 4, then the cylindrical capacity is bigger than pi. So it cannot be, this torus cannot be squeezed into a small cylinder. And yet I can take kind of arbitrarily small volume of a domain containing these points, and kind of the inverse image of this would have arbitrarily small volume, and it would be very, very nice. It would be very symmetric and invariant under the torus section. And yet the Gromov width of it would be very, very small because it has very small volume. So this suggests that the Gromov width and the cylindrical capacity of this example are arbitrarily far away, despite the fact that it's star-shaped and very, very nice. Okay, so why convexity helps? So I can use the classical Jones ellipsoids to show that the Viterbo conjecture almost holds. So a Jones ellipsoid would be the largest ellipsoid contained inside the domain K. And it is known that K is contained inside 2n times the ellipsoid. Okay, so K here is a convex and in R2n. This is a classical Jones ellipsoid tool. And because all capacities coincide for ellipsoids, we get that sort of all capacities of K could not be too far away from each other. So far away up to 4n squared. So it's already demonstrating a very different behavior from star-shaped to convex domain. And one could utilize this philosophy from convex geometries that sort of all convex domains are somewhat similar to ellipsoids in a finer way than just Jones ellipsoid, to actually prove that the Viterbo conjecture holds up to a universal constant for convex domains. So meaning the conjecture holds for a constant independent of the dimension and independent of the domain. So it's also kind of maybe very close to be true. And okay, throughout the years since it was introduced, many private case of this conjecture for specific subclasses of convex domains, the conjecture has been shown. So maybe kind of another indication for it. And another fact I like is that the conjecture holds whenever the domain has S1 symmetry. So if I have a convex domain with S1 symmetry, then I could look at simply the largest ball inside. So the two boundaries must intersect, otherwise I can take simply a larger ball. And now from the S1 symmetry of the ball and my convex domain that I assumed, they intersect along sort of an S1 a loop. And this loop lies inside some complex plane and bounds a disk. And much like the case of the ellipsoid, this disk would be a base for a cylinder containing my convex domain. So again, like the ellipsoid, we get relatively easy here that all capacities should coincide. So the strong Viterbo should hold whenever we have kind of a lot of symmetry, so S1 symmetry. Okay, so another fact is that the EHZ coincide with the Gromov width whenever the maximal, the supremum of a ball embedding is being attained. So whenever I can sort of get the supremum of ball embedding. So why is that? So if I have an embedding of a ball inside my domain, which is attained, so, and also some closed characteristic of the ball lies entirely on the boundary of K. So if I have some closed characteristic of the ball which lies under the image, which takes the ball inside my K, so if the loop lies on the boundary of K, then this loop would be a closed characteristic of K as well. And this would suggest that the EHZ of K is smaller than the one coming from the ball, but since it's contained the ball, it must be equal. So this means that if the loop lies entirely on the boundary, if we have one loop, then we get automatically that the minimal action and the Gromov width coincide. And if no loop lies entirely on the ball, so if I have my domain K and my ball embedding loop looks like something like this, then using like classical theorem, say by Sullivan, or even one can construct by hand, some Hamiltonian function which will push all the points intersecting on the boundary inside. And then we would get kind of maybe something like this, which will allow us to increase the ball embedding, so simply take some scaling of it. So it would be in contradiction to the fact that the Gromov width was assumed to be attained. So this feels like maybe almost a proof, you know, like a reasonable strategy to try and prove the Viterbo conjecture, so attempting to sort of maybe formalize this claim, but as we will see, apparently you cannot kind of make this into a proof. But that was, at least for me, one of the reasons I thought the conjecture should hold. Okay, so next session we will discuss maybe ways to calculate the capacities and a counterexample to Viterbo conjecture. But maybe before we take the break, I can tell you about sort of an interesting connection that the Viterbo conjecture introduced into convex geometry. So kind of very famous conjecture in convex geometry is the Mahler conjecture. So the Mahler conjecture involves centrally symmetric convex domains, so K would now be centrally symmetric. And it's polar, so it's a dual body, which is defined as this. But maybe let's consider an example. So the dual of the ellipsoid would be an ellipsoid with 1 over the radiuses. And so the dual of the ball would be a ball of 1 over the radiuses. And let's say the dual of a simplex would be a simplex, but the dual of the cube would be the cross polytope, so the L1 ball, unique ball. So that's a dual, and in for general domains, yeah, okay, I can just do it here. So if I have some, general domain, and I look at a normal at some point, and I look at the distance from the origin, so that would be h, the height, and the normal, then n over the height would belong to the boundary of k-polar. So this would be maybe an intuitive way to think about k-polar. And this action of associating to every domain it's polar would satisfy that it's order in reversing. So if K is contained in some other convex domain, it means that T polar is contained inside K polar. So it's order reversing. And it's also an involution. So K polar polar, so doing it twice, would bring us back to K. And so the fact that this is in fact the only order in reversing involution over convex domains, let us think about this action as taking 1 over K. And this thing is maybe the motivation or to think about the volume product of the volume of K and the volume of K polar. This quantity would be scaling invariant and also even linear transformation invariant quantity. And it's maybe natural to think whether can we bound this thing. So it's long known that this quantity is maximized for the Euclidean ball and its linear images. However, the lower bound is still open. So it's known as the Mahler conjecture. And it's conjectured that this volume product is being minimized by the cube or its polar, the cross polytope. And it's still wide open. It's known only in private cases. And Mahler Mahler proved it for dimension 2 for the plane. And only in 2020 it was proven in dimension 3. And in more general, it's still open. And why I'm telling you about this is because Viterbo conjecture could imply Mahler conjecture. And more specifically, the Mahler conjecture is in fact equivalent to some special case of Viterbo conjecture, where the idea behind this is if we take some centrally symmetric K and we look at their Lagrangian product, so meaning when K is now in RP and K polar is in RQ, then the minimal action of this type of domain is always 4, regardless of the choice of K. This immediately gives us that the Viterbo conjecture for this type of domain is equivalent to Mahler conjecture. So we get it kind of immediately. And you might want to ask at this point, you said that the sort of conjecture optimal for Viterbo conjecture is balls, but the optimal for the Mahler conjecture should be cubes. So how does these two things fit together? But remembering that here we take Lagrangian product with the dual, they actually fit together pretty nicely, because we get that the Lagrangian product of the cube with the cross polytope using kind of angular momentum coordinates is, from a symplectic point of view, equivalent to the ball. So the two conjectures actually fit together quite nicely from this point of view. And even more, it is long known that the Mahler conjecture is minimized not only if it's true by the cube, but by all kind of Hanner polytope, something called. And perhaps the fact that it has a lot of minimizer is what makes this conjecture somewhat hard, because you cannot sort of find a clear process which converge to the minimums, because you have a lot of minimizers. And perhaps if they are all, from a symplectic point of view, equivalent to a ball, this would be an advantage of this point of view, because if they are all symplecomorphic, then maybe you can find a symplectic process which are all converging to the same one from a symplectic point of view. Coming back? Where we left things last time was that we want to explore this Viterbo conjecture, which try and relates the minimal action with the volume. Maybe one way to try and approach this would be to improve our understanding. So get maybe a bigger class of examples we can compute this capacity or minimal action on. if we want to use the computer to do that, so the way to approximate a convex domain would usually be by a non-smooth thing, so it would be with a polytope. So maybe here let me remark that when restricted to convex domains, then the capacity is continuous. It's not continuous in general, but for convex domains from the monotonicity and homogeneity, one has that it's continuous. So it's defined even for a non-smooth case simply by taking the sort of the supermum. There's only one way to complete it, by taking the supermum of smooth domain inside. But this is not very convenient quantity to work with. And it turns out that it could be generalized to being defined using this Hamiltonian periodic orbit. So remembering that our goal is to take some Hamiltonian on having the domain as a sub-level set, and we are exploring Hamiltonian periodic orbits on its boundary, satisfying the following. And if H is not smooth, so if H is, say, a convex, representing a convex polytope, then we can still think about it this way. But now we don't have a gradient, but we can take sort of the subgradient because it's convex. And now maybe the flow would not be well defined in non-smooth points. But if we require that gamma dot will belong to J times the subgradient, it would be good enough. So we're still minimizing over what we call generalized Hamiltonian periodic orbits. We would still get the capacity, so the value one would get from taking the supermum over smooth domains inside. So this means that we can work with polytopes. And this is sort of the object we want to explore. So instead of requiring that gamma dot would be equal to J times the gradient of H, we now say that gamma dot belongs to J times the subgradient of H. Right? So if we have some convex domain, instead of requiring that it would be J times the normal, now it should be belongs to J times the normal cone. So if I hit a corner, some non-smooth point, I have a choice I could choose, but any choice of a normal from the normal cone would be good, would be a generalized closed characteristic. So I can replace the gradient with subgradient. Things will still work. And it will also coincide with the sort of optimal value, which would be taking kind of a limit of smooth things from it. So it's very workable with quantity. And kind of Clark had a very useful variation principle, which allow us to transform this problem of finding the minimal of closed characteristics to finding the minimal over some functional. So we no longer need to solve an equation. So to find this closed Reb flow of the closed orbits of this vector field. So we are working with the free loop space, but we need to sort of minimize this functional. So this is the transformation of the problem. But the downside of this is that now we have to work with an infinite dimensional space of loops. So it's still maybe not that easy. But luckily, when K is a polytope, that one can do some action rearrangement arguments to show that you can eliminate a lot of the options for this loops, and you only need to consider, because the minimizers should belong to a very finite subset of loops. So we only have the minimizer should be of a simple form, and we can define what simple form is, and we need to minimize our only over this subset. And specifically, it means that if we have a K polytope, we can show that the action minimizer closed characteristic velocities would be normals to the facet, so don't belong to the normal cone, but belong to the actual normals of the facets. And so alternatively would belong to J times K polar. And each of these velocity would be utilized at most once. So we use the velocities at most once. So it gives us a finite set of possible loops to check, and checking the action of each of these options and taking minimum over them give us a combinatorial formula for calculating the capacity of each polytope in every dimension. And of course, this from the continuity, this means that we can compute the capacity of every domain. So we can approximate any domain with a polytope and calculate its capacity. But the downside of this, or the caveat of this algorithm would be such that the complexity of the algorithm will grow as the number of faces will grow. So if we have a very complex polytope, we might not be able to calculate the capacity. So, okay, we can have a new, very large class of polytopes. We can compute the capacity of, but still not all convex domains. So I find that this progress allows us to further study capacities and sort of have a better intuition into how this minimal action behave. And kind of naturally, in view of the conjecture, Viterbo conjecture, what's one do when you have an algorithm to compute is to try and find a counterexample to the conjectures. And we did that, but and we failed to find a counterexample in this way. And moreover, a lot of the attempts to try and find counterexamples using this actually converge to the equality case. So they all converge to the conjectured maximal systolic. So it also kind of helped to maybe reinforce the belief in that conjecture. And so maybe let me describe one such attempt. So one can consider the standard simplex, so the convex hull of the origin and the standard basis, say in dimension 4. And we can understand the dynamics very, very well. The dynamics is relatively simple and it's concrete, so we can study it. And we notice that through the vertices, other than the origin, no characteristic with minimal action passes through. So we can intersect the domain with a half space. So we move this part, and the capacity will not change because the minimal action will remain the same. And because we made the volume smaller and kept the capacity the same, we get a sort of higher systolic ratio. And so we can kind of push this hyperplane further and further until it hits a minimal orbit. And we can do it to all vertices. So through the origin we have one, but we can do it through all others. And we get the domain of this standard simplex intersecting the cube. And this domain, so let's say X, actually have the same capacity to volume ratio as the ball, so 1. And now this domain I cannot improve in the same way, because through every vertex of this domain, one has a close characteristic with minimal action passing through it. So I cannot sort of do the same procedure. I cannot chop the vertices and improve the systolic ratio. And it seems that sort of every perturbation of that domain would make the systolic smaller. So this seems also like a maybe kind of experiments one can do with this formula one has. And this kind of procedure could be generalized into also this kind of smooth domain and lead us to the definition. Oh, I should also mention that around the same time there were another algorithm in dimension 4 to calculate the capacity in a different way due to charges and hatching, and they also did these attempts to find counterexample and kind of came up with very similar results, all converging to the equality case. So coming back to the Zoll notion, so again, borrowing from Riemannian geometry, this symplectic Zoll is defined as a domain having through every point passing a closed characteristic, and all of the closed characteristics have the same orbit. And the same action, sorry. And I'm claiming that if I have a maximizer of the systolic, which is smooth and strictly convex, it must be Zoll. So it must satisfy this condition. Because if it is not Zoll, so if we have some point that no characteristic with minimal action passes through it, I can kind of chop it off in the same manner, make it smaller, and the action will not change, but the volume will become smaller, so I can improve the systolic. So if my domain is smooth and strictly convex, it must be Zoll. And in fact, this notion is being explored and showed that the opposite is also true. So symplectic Zolls are also local maximizer of the systolic. So any small perturbation of symplectic Zolls is also a local maximizer of the systolic. So kind of very strong indication to believe that maybe the global maximizer should be Zoll. And in dimension 4, it was also shown by this group of people in a series of work that these two results, that also symplectic Zolls are equivalent to bolts in dimension 4. Let me remark that when we go to the non-smooth case, things become a bit more difficult. So if I look at a non-smooth domain, then, since my dynamic is not well defined at the non-smooth points, I have a choice of the vector field, then it may be a bit harder to define Zoll because the dynamic is not well defined, but I can still define it maybe as there exists a closed characteristic with minimal action through every point. Right? I have a choice of normals which will make it. But under that definition, then also the standard cube would be Zoll. But the standard cube is not symplectomorphic to the ball and have very bad systolic ratio. So we see here somewhat of a different behavior already between the smooth and sort of the non-smooth case. So these results are only for smooth. That's why it's not sort of proving the conjecture. Okay, so that was sort of one attempt to tackle the conjecture through trying and finding the dynamical properties that a maximizer should have. But another way to try and tackle it would be to try and define convexity using intrinsic symplectic properties. So trying and understanding what is the symplectic properties that convex domains satisfy that cause them to behave in a special way. So what the symplectic property we need to use in order to show the conjecture. And an attempt for that is something called dynamically convex, which is coming only from the dynamics on the boundary of domains. So it's a definition only depending on the dynamics. And specifically, it measures, very roughly speaking, sort of that how much the neighboring orbits of a closed orbit spin around the orbits. And it is known that for convex domains, they have to spin at least some amount. And so this would suggest that dynamically convex are all convex domains are dynamically convex. So that was known. And it was thought or hoped that perhaps this property, this having dynamically convex is enough to guarantee that the domains satisfy the special properties that convex domains satisfy. Or even a somewhat more far-reaching hope would be that every dynamically convex domain should be have a symplectic image which is convex. So maybe it's exactly equivalent. But then Abundandolo, Barney, and Herajnovic and Salomeo showed that they constructed an example which is dynamically convex and have a systolic 2, so bigger than the ball. So this means that there is a dynamically convex example which violates Viterbo conjecture. So this means that either Viterbo conjecture, the thought after this result was kind of that either Viterbo conjecture doesn't hold, or that dynamically convex are not equivalent to being convex. So very good. The exact thing they did was construct an example for a dynamically convex which violates Viterbo. So they could both be wrong, and in fact they are both wrong. But yeah, the thought when this came out was that it's one or the other. But as I said, like 2 years ago, Chajas and Etmeyer constructed an example for a dynamically convex which is not convex. But when this came out, we didn't know that Viterbo doesn't hold, and it was somewhat another indication to maybe why Viterbo should hold. Okay, so as I said, actually now we know that also Viterbo conjecture doesn't hold. This was done recently by myself and Osterver, and yeah, this implies that the two options are incorrect, and maybe we really don't know much. Okay, so how does this counterexample look like? So it's an explicit, which we'll describe later, product of two domains in dimension 2, so a very explicit one. And the systolic is, however, slightly bigger than 1. So bigger by just a little bit, but still bigger. And this means that the Viterbo conjecture doesn't hold in dimension 4. And one could take this to be a counterexample in any dimension using some tensor power trick. But a bit more delicately, so instead of using the usual product, one needs to use something called p products. So I guess it's best explained by the picture. So here, the top row is the p product of a triangle and a line segment, and the lower row is the p product of a disk and a line segment. And it moves from the one product, which is just the convex hull of the two domains lying in orthogonal spaces. The two product is kind of ballish thing. And as p goes to infinity, it becomes the Cartesian product of the two domains. Okay, so using these products and keeping track on how the capacity changes and how the volume changes, one could construct a counterexample, form a counterexample in dimension 4 in every dimension. It's coming from the fact that the systolic of k times 2 t would be equal to this product of systolic of k and the systolic of t if the capacity is equal. And I'm using always the EHZ here, the minimal action capacity. Okay, so I need to take the two products instead of the usual. But this may be unsatisfactory because we had like the nice product here, and this would ruin the structure if k and t are products. So it turns out that I can do something a bit better. So I can take the systolic of k1 times k2 times now Lagrangian product of t1 times 1 now, t2. And that would be equal to the product of the systolics of the two domains. Lagrangian, yeah? And again, under the assumption that their capacity were equal under the. Okay, so this way you can get a counterexample in every dimension in two different ways. Okay, as the counterexample is of this form, which is very, very special of taking Lagrangian products, maybe let me discuss how dynamics looks in this case. So it's in close relation to billiards. And so the Hamiltonian in this case will look as the maximum of the norms of these two domains. And the norm here is just the norm such that the domain K would be a unit ball. So it's an infimum of a positive number such that X belongs to R. Okay? So if I have some K and T, how will the Hamiltonian dynamic would look like? So I'm starting from some point on the boundary. So it would be on the boundary of T, of K here and in the interior of T. And then I look at the normal to the domain, which is just the normal to K. And then I move in J times the normal, so it moves kind of in minus the normal, but in T. So until I hit the boundary of T. And here I hit a corner, so I get the normal cone and not just one option. So I choose one of the normals in the normal cone, any of them. So here it's chosen some direction. And I move in J times it, which is just moving in K in the same direction. So I move in that direction in K, again, until I hit the boundary. And then I look at the normal, and I move in minus the normal in T, till I hit the boundary, and so on, and so forth. And this dynamics is actually the same one would get if we would take the Minkowski billiard in K with the geometry coming from T. So what do I mean by that? So if I'm considering the usual billiards, so the reflection law would be that the two angles of incident and reflection are equal, then it comes from sort of maximizing the point Q2, QT on the boundary of the length between Q2 and Q1 and Q3 to Q2. So finding optimization for Q2 under this law would give us the usual reflection law of billiards. So I can choose any of the vectors belonging to the normal cone. So yeah, the normal cone is just a positive combination of normals. No, so the minimizer would be to choose Q2 to be Q1, right? And that would be a line. So it's the maximum. And I would get sort of this behavior. In order to get this, I need to replace the norm by the T-polar norm. So the norm such that T-polar would be the unit pole. So if I take this optimization now, I would get the reflection law coming from the Hamiltonian, coming from the product. So this dynamic is very, very special and relates to kind of Minkowski billiards, which are defined to a Minkowski norm or even a Finsler metric. Moreover, the action, so the action of the orbit in dimension 4 would be in corresponding to the length of the billiard when thinking about it in T with respect to the T norm length. So if I measure my distances with this norm, I would get that the length is in corresponding to the action of the okay, and kind of a very useful point of view in billiards is a Bézic and Bézic approach, which tells us that this, to find the minimal billiard inside a some table, so in our philosophy, K would be the table and T would give us the geometry, then it's enough to look on all curves which could not be translated into the interior of the domain. So, for instance, if I have a triangle with an angle larger than 190, then if I look at the minimal billiard trajectory, it cannot be translated into the interior, and this would actually be the minimized billiard with the standard one. And if I look at the equilateral triangle, then again I have the same orbit, but it will not be the minimizer. The minimizer would actually be going between the middle of the edges, which is also a curve which cannot be translated into the interior. So this is kind of a new law to try and find minimal billiards, and it's also can be shown that it's enough to consider billiards with at most n+1 hitting bouncing points. Yeah. So where n is the dimension of K or T. Okay, and so this kind of philosophy tells me that if I normalize things such that the capacity of K times 2T is 1, and I look at sort of all curves such that their length, when I measure it with respect to T polar, then for any curve in this domain, I can find a translation which will take it into K. So gamma plus x belongs to K. Yeah? So otherwise I could, the capacity would not be 1. And so if I'm playing the game of trying to improve the systolic, so I want to take capacity, fix the capacity, and take the volume to be as smaller as possible, then I want to find what's the best K fixing the geometry, fixing T. Then I can imagine that K should be the convex hull of such gammas over all possible translations. So I'm going through all translation, and I'm trying to minimize the volume of the convex hull of these translations. But this is like an infinite thing, and maybe very, very hard. But it turns out that you don't actually need to go through all possible orbit, but you can narrow it down to kind of a finite subset of loops. So if I can find some K which is minimizing over the convex hull over all translations, the area of it is minimized by over all translations of the gammas, and the gammas are minimal orbits of this K times T, then this K is optimal for T. And moreover, if I have equality with a different K, so if I can translate them in a way which will also be optimized, then the curves are the same curves that I started from. And so maybe it's easier to see an example. So if I'm considering the cube, then I have two kind of natural billiard trajectories. So I have the red one, which is going through up and down, so using the normals to this facet and the normal to that facet. So that would give me going up and down the red, one periodic orbit, and the same from left to right and back. So that would be the red one. And now I can take the convex hull of these two, and it's minimizing over the convex hull of these two. And so it would be optimal for this cube. And so this is kind of what this observation is trying to say. And kind of in view of this formula for the capacities of convex polytopes, we have a very natural candidates for this, right? So we want to say that the gammas we are interested in are kind of the one which utilize normals to the polytope. So if T is a polytope, I want to look only on billiards which come from velocity utilizing the normals to the facets and not using the normal cones. And I'm taking, okay, all possibilities of choices for them and all orders for choices of them, and this gives me a finite set of curves. And now I'm playing the game of trying to minimize the area of the convex hull of these loops. Okay, so this is what we are doing here. So we take all the possibilities, because of the symmetry, we only have two. And we get these two ones. And now I want to look about all translation of these two and the convex hull. So it apparently stays the same, no matter how we move the two, as long as they intersect. Right? The area would stay the same. And so all of these two, as long as they intersect, have the same systolic. And moreover, these two would be minimizers of this domain. And in fact, it is known that all of these domains, the product of the cube with this type of things, are all symplectomorphic to the ball. So are all symplectic images of the ball, no matter how we move these lines. Okay, and so one can ask what happens if I take, instead of the cube, I'm taking a triangle. So if I look at say this triangle, then I get all curves with the same length would be these two. So maybe another color. And kind of the minimizers under this would be, oh, it doesn't look like this, but some sort of hexagons. Oh, it's bad drawing, sorry. So they would all be hexagons. Maybe I will erase this because it's a bad drawing. But what happens when we look at a pentagon? So if we look at a pentagon, then now what are all our options to get a vanishing linear combination of normals? So if we take one normal, so say to the upper one, then we can choose the two opposite normals. This would give us a single vanishing linear combination. And then we scale it such it would be with length 1. And we add it to a pile of triangles. And we also have a different choice of order, so we can choose it a different order, and we get another triangle. And we can do this to every normal of the pentagon. And in the overall, we will get 10 triangles. And here they are represented, all 10 triangles. And now our game is to try and kind of minimize the area over all translations of these 10 triangles. And when kind of we try and do that, we get that actually these triangles could be translated into being a pentagon, a regular pentagon itself, the same one, rotated by 90 degrees. And sort of this would be sort of the optimal, the minimizing area of overall translations of these 10 triangles. And when we do a kind of analysis of the areas and then actions that one gets in this case, this turns out to be a counterexample to Viterbo's conjecture. So indeed, the product of the pentagon and rotated pentagon by 90 degrees is a counterexample to Viterbo. And the minimal action of this example would be achieved by the triangles we saw before. So the ones coming from edges, adjacent edges. But there will also be additional minimizers. So there would be, for example, 2 bounces, which will minimize the action. So going from one vertex to another along the diagonal will also give us a minimizer. Okay, so maybe let's explore the dynamics here a bit. So we want to consider the sort of the generic case. So we start with some point on the boundary, and we move, want to see how the dynamics behave. So we can focus only on one, and remember that the dynamics is being dictated by our other pentagon. So remembering this, this is the pentagon determining the reflection law. And so our normals are just 5 possibilities. And since this is a rotated pentagon by 90 degrees, this means that if we move in one of these 5 velocities, we move in a direction which is parallel to one of the edges of the pentagon. And moreover, because these pentagons contain some disk and the normals coincide, all the facets touch the inscribed circle, then the reflection law in this case would be the same as the Euclidean one. So we have a standard reflection law, and in that case there is a very nice trick one can use, which is the unfolding. So I'm moving, and now the reflection could be viewed as, instead of reflecting the billiard, I can reflect the pentagon through the edge it hits and continue in a straight line. And sort of this point of view allow me to see that all orbits would be closed. Yeah, it's not too hard to see this way, because no matter which point I start through on the edge 0, 4, I will always be hitting it again after a while. And moreover, all of these orbits would have the same length. Okay, so if I try and shift the different starting points, I would get closed orbits all with the same length, with the exception being when I'm on the middle edge, and then I would be closed after half of the length. Okay, and so what happens if I'm moving my starting point not in the same direction, but not on the edge 0, 4, but on the edge 4, 3? Then I would get a very similar image. So I would also have, like the reflection would be slightly different, but I would also get that every point is closed and that they all have the same length, but to the middle point, which will have half the length. So this would be the generic behavior. So if I'm starting from a general point on the boundary, this is how it would look. And this relates to the concept of symplectic Besse, which is again borrowing from Riemannian geometry, saying that I want all closed orbits to be, all characteristics to be closed, so all orbits to be closed, but now I don't require that they will all have the same action. So this is called Besse, and again in the smooth case in dimension 4, the only Besse are ellipsoids, rational ellipsoids, but here in the smooth case, this is clearly no longer the case. And let me remark that none of these orbits that we've described here are actually the minimizing. So the minimizing would be different. So for example, they would be these diagonal ones. So so this one, and if I'm recalling my Bézic and Bézic approach, all sort of 2 bounces which could not be translated into the interior are kind of from one vertex to the opposite edge and back. So all the curves looking like this. And it turns out that all of these two bounces actually have the same length when measured with respect to this pentagon. So any one of these two bounces is a minimizer. And there's also 3 bounces minimizing. So they generally could be described as if I'm fixing the point on the edge, the upper edge of this one, and I'm drawing a cone going through a parallel line to the adjacent edges. This cone, this edge, and I'm looking at all clockwise triangle inside this, trapped inside this cone. Then each one of these triangles would be a minimizer. For instance, this one. So it could be a regular one, so like the blue one here, which goes through some points. But it could also be more degenerate, so going to the edge and then going along the edge and going back through the diagonal. So I have a lot of types of minimizers, but let me remark that all of the minimizers must pass through a vertex. This is sort of the conclusion of this, because we saw that sort of through generic points, or through points which don't go through a vertex, we get a bigger action than any of these ones. So here we may not see it, but in these triangles, for example, we must hit a vertex in T in this case. So for example, for this. Yes. And this characterization is also containing the triangles, the original one we started from. We minimize the area because we can push sort of this point to the vertex V2, and then we would get sort of the triangle that we translated to get this domain. Okay, so that sort of characterized the minimizing orbits. I should say that sort of one might expect that solving the conjecture would maybe solve some stuff, but it looks like it leaves us with even more questions than before. So, okay, trivially, what's the biggest value? But maybe more interestingly would be to find a kind of dynamical characterization that the maximal value of the systolic should satisfy. So can we characterize it? And let me remark that using these John ellipsoids and the compactness that convex domain have, if they are inside some bounded set, then we know that this maximizer is attained. So the maximum of the systolic over convex is attained. And so it's a very natural thing to ask how it looks from a dynamical point of view. So the Zoll was very, very natural, but now it looks like it's maybe not true, but maybe finding a new kind of possible characterization for that. And sort of a lot of evidence that one has in favor of the conjecture, the Viterbo conjecture, might suggest that despite the fact that we have now a counterexample, there might still be a very large class of convex domain that the conjecture still holds for them. And it would be very interesting to try and characterize it. And especially in kind of a view of the Mahler conjecture, if one can show that the Viterbo conjecture holds for centrally symmetric, then perhaps one could get still Mahler using symplectic methods. So it's worthwhile. And again, maybe kind of very natural thing would be to try and characterize convexity from a symplectic point of view. So going back to the question, can one identify convexity or the properties that convexity satisfy which cause them to behave in such a special way, such a different way than other convex domains, than other symplectic manifolds? And so the characterization of the rigidity phenomenon that prevent domains from being convex might be a very worthwhile question. And it leaves us with the question, as now we know that Viterbo conjecture doesn't hold for convex and for dynamically convex, how really different these two sets are. So, okay, perhaps there are examples for dynamical elements which are not convex, but perhaps they're actually not that different from a dynamical point of view. And kind of another question is how many capacities one has. So since we contradicted the weak Viterbo conjecture, we also get that the Gromov width and the cylindrical capacity are not equal. So it's a strong Viterbo conjecture doesn't hold as well. But still one can ask how many capacities there are now on convex domains. So of course one could look at the average of two capacities. So 1 minus lambda, say the Gromov width, and lambda, the cylindrical capacity. This would also be a normalized capacity. And one could look at also their harmonic mean or another function, maybe the maximum of the two, another minimum, any monotone and homogeneous function. But okay, up to these actions, how many capacities can one find? I mean, are there only two? And I should remark that concluding like a lot of works in that area, so in dimension 4, it is known that this EHZ, which a lot of capacities are equal to, is actually equal to the cylindrical capacity. And this is Bondandalo, Edmeyer, and Kang. And it's somewhat recent. And so this means that to this day, we only know of two capacities in dimension 4. So the Gromov width and this one. And so it would be interesting to say whether these are actually the only two up to these trivial actions. And going back to symplectic bases, so it's very natural to expect that the extremizer of the systolic should be bases, so it should be sort of utilizing every point on the boundary from a dynamical point of view. But the study of maybe non-smooth bases seems to be maybe not that far, so it would be interesting to do that. And one could get that using any regular polygon times its rotation. So for instance, if we look at the cube times the cube, this would be a basin, in fact a Zoll. And if we look at the triangle times the rotated triangle, this is actually an ellipsoid, known to be ellipsoid. So this is Ostrov and Ramos Sepe recently. And now the pentagon times pentagon seem to be. And yeah, this may be a good branch to investigate. There are many other questions, but I should stop here.